Hi everyone, and welcome to another video in a series of videos in which we're talking about different types of statistical analyses. Today, we're specifically going to be looking at survival analysis, which is actually a branch of statistics and epidemiology, which regards the analysis of survival data. There's a whole bunch of different types of analyses within this branch that you can use, but today we're going to look at three specifically, namely the Kaplan-Meier curves, the Cox regression, and a Cox regression with a time-dependent covariate. Now, for these analyses, or for the first two specifically, we'll be using this data set that I have open right here, which regards data on whether or not people died, whether they were smokers, yes or no, and what their gender was. And in addition to knowing if they died or not, we also know at which time it happened. So after how much time did somebody actually die or was lost to follow-up during the research. And that is, of course, the typical characteristic of survival data. So let's take a look at the variables that we have in this data set. So we know what we're working with. So we have our patient ID, so the unique identifier of each patient in this data set. We have the status, which consists of censored, which is a survival jargon for somebody who's being lost to follow-up. So this could be due to multiple reasons. Maybe somebody moved and wasn't able to participate in the research anymore. Maybe somebody doesn't want to participate in the research anymore. What we know is that up until that point, that person was still alive. And what happened after that with that person, we don't know. And we stop counting the time from that moment on. And of course, we also have the status deceased. So if somebody died and after how much time it happened. So, and then of course we have the time variable indicating at which time point somebody either was censored or deceased. We have the gender, which consists of 0 and 1, respectively male and female. And we also have smoking, respectively non-smoker and smoker, coded as 0 and 1. All right, let's get started with the Kaplan-Meier estimate, which we will find under Analyze, Survival, Kaplan-Meier. And we'll get a new screen in which you'll have to input a couple of things. So the first thing that we'll have to do is we'll have to define the time, obviously. So that is easy. We just input time in the time box. We have to input the status, which is the outcome. So it doesn't necessarily always have to be called status, but it's the outcome of interest that you want to analyze. And besides of defining the status variable, you also have to define which value is actually an event. So in our case, our event of interest is whether somebody deceased. And that was coded as 1. So we have to define value 1 as an event. Next to that, we will go to options and we will ask for the survival plot. This will give us the actual Kaplan-Meijer Curve. And with that, we will start to analyze the survival times for the entire cohort. So let's get right into it. Let's paste away to the syntax and let's run the syntax and let's take a look at what we get. So the first table, we get the case processing summary, which shows us an overview of how many observations are included in our analysis. In this case, that equals 100. And next to that, we also see how many of those 100 observations experienced an event, so whether or not they died, 76 in this case, and how many were lost to follow-up or censored in survival jargon, 24 in this case, so 24% of the cohort was censored. Now let's go down to the survival table, which is where the interesting stuff happens. So in the survival table, what we see is the development of the cumulative survival fraction, which is the basis of survival analysis. It's the development of the survival fraction. So of course, at the beginning of the research, the survival fraction starts at 1 because the chances of survival at the very first moment of the research in this case is 1. Everyone is still alive, so the chances of survival are 1. So if we look at the table, the first thing that we see is that in time point 5, one person is censored. But remember that censoring doesn't actually develop your survival fraction because we don't know whether this person died or not. So we cannot actually have our survival fraction develop. So it stays 1. But what it does do is that it changes the amount of total people that we still have left in our cohort, 99 in this case. So we lose 1 due to follow-up. So it doesn't change the survival fraction, but it does change the total amount of people that we have left. Now let's move on to time point 6, in which the first thing actually happens, and there somebody does die. So at time point 6, one person dies, one individual dies, which means that our proportion is changing now, because the survival fraction of this particular period is that one person out of the 99 cases that were remaining in this time period died, meaning that the proportion of survival is 98 over 99. Which in this case results in an estimate of 0.99. And we see that up until this point, the cumulative amount of events is 1, because so far one person has died. Now let's move on to the next point to illustrate what happens next. So once again, somebody dies at time point 8. So now we have, of course, 2 cumulative events. But for this particular time period, 1 out of the then 98 remaining cases will have died. So the survival fraction for that particular year is 97 over 98. And we multiply that fraction with the proportion of the preceding period. So in this case, that would be 0.99 times 97 over 98. And that results in this case in 0.98. So as you can see, this is a very long process of calculating how many people survive and multiplying that fraction with the proportion of the preceding year, which is a lot of work and results into a very long table. But what you can see is that as events start to happening, as people start to die, the survival fraction goes down ever so slightly until we go all the way down and the survival fraction equals 0. Meaning that everyone in this cohort has then died. Nobody's left. Now, this is obviously not the most easy way of interpreting the development of this survival time. So what we generally do is we take this and we plot it into a graph. And that results in what we find at the bottom output, the Kaplan-Meier curve. So what you can see here is on the y-axis, we have the cumulative survival proportion, which we saw was developing all the way down to 0 earlier in those tables. And on the x-axis, we have the time in years. In this case, could also be weeks, days, or whatever it is that you're looking at. In this case, it's years. And what we can see indeed is that that cumulative survival proportion goes down ever so slightly over the years. So as the years pass, people start to die, obviously. And the cumulative survival proportion decreases all the way down, in this case, to 0. So above the graph, we see another interesting table, which is the means and medians for survival time. And when we look at the median survival time, which is the middle of this graph, so to speak, I'll get to what that is in a second, equals 41. So the median survival time of this particular cohort is 41. Now, the median survival time is the amount of years, in this case, that have passed when the survival fraction equals a half. So when you're in the middle of that curve. And in this case, when we look at the middle, 0.5, we see that that roughly equals 41 indeed, which we can then read as the median. The reason we use the median is because these graphs or these distributions are not always symmetrical. So therefore, the median is more often a better indication of the middle of this graph. And therefore, the average or the mean is not always an informative measure. So that's why we usually report or we look at the median. So that's what we do in this case. And it's, of course, reported with its standard error as well as the confidence intervals around that median. Now, generally speaking, when we are, as health scientists or as epidemiologists, we're not often interested in what is the development of this cumulative survival over time of this entire cohort. No, what we're actually interested in is usually how do these survival times look for different subpopulations. So, for instance, do these curves look different for, of course, smokers and non-smokers? So that is exactly what we're going to be looking at now. So how do we analyze this for subpopulations? It's very simple. We go back to analyze, back to the Kaplan-Meier curve, and instead of moving on with the procedure as we just did, we add smoking or some other type of factor as our factor variable. And what that will do is we'll generate two separate curves for these subpopulations. We can also see that the compare factor option has just become available. So we'll press that, and we will also ask for a test statistic, namely the log rank test. The log rank test, what it will do is it will test whether the survival curves that we are going to plot in a second are actually equal. So if the survival time for smokers and non-smokers is the same. And then of course the alternative is that they are in fact different, so they're not the same. So let's paste away and go to our syntaxes and run that, obviously. And we will actually get the exact same output. So we'll have the case processing summary in which we see information that we had previously, namely we had 100 observations of which 76 had an event and 24 were lost to follow-up or censored. But now we see that also for smokers and non-smokers separately. So we see that there are in fact in this research 30 smokers, 70 non-smokers, and of the 30 smokers, 24 were recorded to have an event, 6 of them were censored, and out of the non-smokers, 52 had an event and 18 were censored. We get, once again, the survival tables, the long tables, but now split up for smokers and non-smokers. But we will get straight to the nitty-gritty, namely the Kaplan-Meier curves. And this time, what we can see is that we have not one, but two curves separate for smokers and non-smokers. And of course, we can already see quite striking differences. The curve for smokers develops downward faster, or in earlier years, than it does for non-smokers, which of course follows logically from what we know today of the adverse effects of smoking. And we can see it also quite nicely in the means and medians for survival time tables. We can see the median survival time for smokers is merely 26 years, whereas for non-smokers, it's actually 47 years. It's quite a big difference. What we can also see is this log rank test is strongly significant. In fact, the log rank test, what it basically does is it looks at the expected events under a true null hypothesis, and it contrasts it to what is actually observed within the groups of smokers and non-smokers. And it statistically tests this in the same way as a normal, quote-unquote, normal chi-squared test does. And in fact, it also follows a chi-square distributed test statistic with some amount of degrees of freedom. In this case, we have two groups. We lose 1 degree of freedom, and so we are left with 1. And as you know, with a chi-square distributed test statistic and a number of degrees of freedom, we can find a probability density. And in this case, that probability density is very tiny. It's less than 0.001, meaning that we can reject the null hypothesis that the survival times or the survival curves are the same for smokers and non-smokers, and that they are in fact different. So we accept the alternative that they're different. Now that is all well and interesting, but generally speaking, we want to take it even a step further. Namely, what do we want to do? We want to know what is the difference between these subgroups or these subpopulations. Is there some factor that we can ascribe to this difference? So with this log rank test, the only answer that we get is yes, there is indeed a difference. But how big that difference is, we do not know. And therefore, we often resort to regression. And surprise, survival analysis has also got its own type of regression analysis, and it's called Cox regression. And that is what we'll get into in this next part of the video. So Cox regression is actually very closely related to logistic regression, as it uses a logarithmic transformation of the hazard function, which is also kind of closely related to how we interpret the logistic regression as odds ratios. But in this time, we interpret it in terms of hazard ratios. So let's get into it. We'll go to analyze. We'll go to survival, not regression, Cox regression. And we get a similar screen in which we have to define a couple of things. Since we are doing survival analysis, we have to go to time, obviously. We have to input the status again. we have to define the event, which was 1. And we have to enter covariates. In this case, we want to know what the differences are, the relationship between dying and smoking over time. And we'll ask for the confidence intervals here under options, continue, paste, and let's take a look at what that does. So we get some output. Some of it is a little bit similar to what we saw with logistic regression. So let's get into it. So we have the case processing summary, which we saw earlier. I'm not going to get into it, but it basically shows you once again how many observations there are in the analysis and how many got an event and how many were censored. In block 0, the beginning block, we see actually the -2 log likelihood, the omnibus test of model coefficients, which is similar to what we saw with logistic regression. Actually, Cox regression is estimated in a similar way with maximum likelihood estimation. And remember, with maximum likelihood estimation, we estimated predicted probabilities on the outcome, and we did that in such a way that the product of all these estimated probabilities is the maximum, is maximized. So we maximize the likelihood function so that the model is the most likely. And we do that first for a model in which we do not include our variable of interest, in this case, smoking. And we see that the value for the -2 log likelihood equals 554.341. Then we put smoking into our model. We estimate it in such a way that the likelihood function is maximized. And what we find here is that the -2 log likelihood equals 535.335, which in fact, it improves because the -2 log likelihood decreases. In fact, a perfect model would have a -2 log likelihood of 0, because that would indicate that the probability of the model would be 1. So as it decreases, the model gets better. So what we then do is we take the difference of these 2 log likelihoods, which is subtracting them from one another, resulting into the log likelihood ratio, remember. And the log likelihood ratio, in fact, follows a chi-square distribution. So we see here the chi-square, the log likelihood ratio is 24.653. With 1 degree of freedom, the amount of degrees of freedom is equal to the difference in parameters between the two models that are compared. So in fact, we have an empty model, there's no covariate, and in the new model, we enter 1 parameter, meaning that we have 1 degree of freedom for the log likelihood ratio. And with that, we can, of course, find a probability density, which is very tiny, minus 0. Or lower than 0.001. Now let's get to the variables in the equation, which is the same as we saw with logistic regression, but there is one striking difference, and that is that there is no constant. And the reason for this is that with Cox regression, the constant is actually the baseline hazard at a given time point. We're looking over time, remember. So as you know, the baseline hazard at a time point is different. It's not the same across time points. So depending on which time point you're looking at, the baseline hazard on the outcome is going to be different because it develops over time. What doesn't develop, or what we assume to not develop over time, is the difference in hazard at any given time point. In fact, this is a very important assumption with Cox regression models, and it's called the proportional hazard assumption. And it assumes that over time, the hazard on, in this case, dying, is constant over time between smokers and non-smokers. So at any given time point, the hazard on dying for smokers as compared to non-smokers is the same, regardless of which time point you're looking at. And of course, we have to make sure that we actually meet this assumption in order for this output to be reliable. In this case, we do meet that assumption. And when we go to analyzing with a time-dependent growth rate, I'll show you when we do not meet this assumption, actually. So let's get further into interpreting this output. We see, of course, a regression coefficient, which is 1.221. And this coefficient is actually the difference in logarithmic hazard between smokers and non-smokers on the outcome dying. We see the standard error, we see Wald testing, which is similar to what we saw with logistic regression. It leads us to the same conclusion that we had with the Omnibus test, which is strongly significant, indicating that there is some relationship between smoking and dying over time. We see an exponent b, which is the exponent of the regression coefficient, and it is interpreted not in odds ratios, but in hazard ratios. It's interpreted as follows. The hazard on dying for smokers as compared to non-smokers is 3.392 times larger at any given moment in time. So once again, we interpret this hazard ratio as being constant over time. So no matter which time point you look at, the hazard on dying for smokers as compared to non-smokers is always the same. And that's important. And of course, we need to meet that assumption in order to rely on this interpretation for it to be valid. And of course, it comes also with the respective confidence interval. So with 95% confidence, the real hazard ratio falls somewhere, or is estimated to fall somewhere between the bounds of this interval.